Hi, my name's Casey.
And I'm Tyla, and our topic for our final project is rotation.
So you see rotation in nearly every machine. You use it every time you open a beverage can with a pull tab, and you pay to experience it every time you go to an amusement park. Rotation is the key to many fun activities, such as hitting a long drive in golf. The ball needs to rotate in order for the air to keep it aloft longer, and throwing a curveball in baseball. The ball needs to rotate in order for the air to push it left or right. Rotation is also the key to more serious matters, such as metal failure and aging airplanes.
We began our discussion of rotation by defining the variables for the motion. The variables for rotation are similar to those for one-dimensional motion. An important special situation is where the acceleration, here the rotational acceleration, is constant. Newton's second law can be written for rotational motion, but we must use a new quantity called torque instead of just force. Work and the work kinetic energy theorem can also be applied to rotational motion, but we must use a new quantity called rotational inertia instead of just mass.
So we're specifically going to be talking about rotational variables. A rigid body is a body that can rotate with all its parts locked together and without any change in its shape. A fixed axis means that the rotation occurs about an axis that does not move. Thus, we shall not examine an object like the sun, because the parts of the sun, a ball of gas, are not locked together. We also shall not examine an object like a bowling ball rolling along a lane, because the ball rotates about a moving axis. The ball's motion is a mixture of rotation and translation.
In rotation about a fixed axis, it contains an axis of rotation and a rotation axis. In pure rotation, every point of the body moves in a circle whose center line on the axis of rotation, and every point moves through the same angle during a particular time interval. In pure translation, every point of the body moves in a straight line, and every point moves through the same linear distance during a particular time interval.
So now we're going to be talking about angular position. So this figure here is before this body or the object moves, and this will be after. So in this figure, it shows the reference line fixed in the body, perpendicular to the rotation axis and rotating with the body. The angular position of this line is the angle of the line relative to a fixed direction, which we take as the zero angular position. In this second figure, the angular position angle is measured relative to the positive direction of the x-axis. So angle equals S over R, where S is the length of a circular arc that extends from the x-axis, the zero angular position, to the reference line, and the R is the radius of the circle.
The arc length change in S is the distance traveled along a circular path. R is the radius of curvature of the circular path. We know that for one complete revolution, the arc length is the circumference of a circle of radius R. The circumference of a circle is 2 pi r. Thus, for one complete revolution, the rotation angle is this equation, which can also be interpreted as this. This result is for the basis for defining the units used to measure rotation angles to be radius rad, defined so that 2 pi rad equals 1 revolution. If change in angle equals 2 pi rad, then the CD has made one complete revolution, and every point on the CD is back at its original position. Because there are 360 degrees in a circle, or one revolution, the relationship between radius and degrees is thus 2 pi rad equals 360 degrees, so that 1 rad equals 360 degrees divided by 2 pi, which equals 57.3
So now we're going to be talking about a concept called moment of inertia, and it is the name given to rotational inertia, the rotational analog of mass for linear motion. It appears in the relationships for the dynamics of rotational motion. The moment of inertia must be specified with respect to a chosen axis of rotation. For a point mass, the moment of inertia is just the mass times the square of perpendicular distance to the rotation axis. So I equals mr squared. That point mass relationship becomes the basis for all the moments of inertia, since any object can be built up from a collection of mass points. So when dealing with inertia, you need to change the equation depending on the object that you're using and trying to measure. So this one here is a solid cylinder or disc symmetry axis. So when you're going this way, this one here is hoop about symmetry axis, solid sphere, This one's solid cylinder central diameter, hoop about diameter, thin spherical shell, rod about center, it's going upwards, rod about end when it's going upwards just on the side, and within the equations that have an L, the L stands for length.
This is an example of moment of inertia for a rod. So the example is, for a uniform rod with a mass of 5 kilograms and a length of 4 meters, calculate the moment of inertia around its center of mass. So the equation for a rod is I for inertia equals 1 over 12 ml squared. So in this case, we have mass is 5 kilograms and length is 4 meters. So 1 divided by 12 is 0.083. The mass is 5, and length squared is 16. This gives us a final inertia of 6.64 kilograms squared.
So that concludes our video project for today. We first learned about angular position, where angle equals S over R, and we learned how to find the arc of a circle.
And then we learned about the common measurements of inertia and the 8 different equations that go along with inertia, followed by an example of inertia around center mass of an object, and the object we used in that example was a rod.
So thanks for watching. Hopefully now you have a better idea of rotation in physics.